So first of all, thank everyone for the very kind invitation. I guess it's clear what I'm gonna be talking about today. I'm gonna be talking about properties of low-rankness that arise in deep learning, together with their computational implications. My background is mainly numerics, so I've been working in the past years on trying to exploit rank properties in neural networks to speed up training and to save in terms of memory. So first of all, I would like to start a bit on the setting and the notation so that everyone is on the same page. Throughout the entire talk, I'm gonna be considering feed-forward neural networks, which we think for a classification problem on a fixed data set that we call XY. And the data set is the classification task is a classification task with big K classes. And so we stack essentially all our data points on columns of a matrix X, and the points are represented as vectors in Rn0. And we stack our representation of the labels of the classification problem in a matrix. And we consider an architecture which is feed-forward, as already said, which essentially we calculate the features of the L+1 layer by just applying an entry-wise nonlinear activation function and a linear function applied to the previous feature matrix. So essentially, this is just a feed-forward neural network written in recursive form. Z0 is our dataset X, and so these Zi here are the feature matrices, which lie in some space of matrices, space of matrices of dimension ni times big N, where n big N is the number of data points, and these matrices here are the correct sizes. Without loss of generality, for the entire talk, I'm gonna be denoting for X and also for intermediate layers the columns of these matrices here with two indices, one below and one above. The one below is indicating let's say it's an index indicating the point, and the one above it's indicating in which class these points stay. So, and without loss of generality, we can order them. So we have the first n1 columns of X, which correspond to points with label 1. The second block corresponds with point with label 2, and etc. Up to the last one with label K. And since it's a classification problem, we can think of Y, for example, to have columns, labels encoded as in one opt-encoding form. So essentially, the columns of Y are canonical basis vectors. Okay, this is the setting, and this is the notation for the entire paper. Now I would like to start talking about a bit of motivation of this work. A strong motivation of what I'm going to be talking about now was an observation done in 2019. This paper here, the lottery ticket hypothesis, in which the authors essentially observed that for a big number of deep learning problems, the number of parameters is essentially overestimated. We are overkilling in the sense that, as you can see in this plot here, for example, we're plotting the percentage of weight remaining. All the rest are set to 0 against the accuracy, so a metric, for example, of a classification task. And as we can see here, 100% means that essentially all entries of all matrices of the neural networks are non-zero. And as we go on, we arrive to around just 2% of the weights of the entries of the matrices, essentially, which are non-zero, which are 0. Sorry, 2% which are non-zero. And the accuracy of the classification task remains essentially unchanged. There is an extremely slow decaying of the accuracy as a function of the percentage of weight remaining. So essentially, this is telling us that we can set the majority of entries of these matrices to 0 without affecting that much the performance. A second observation that has been done, and it's a question that I've been working on since the beginning of my PhD, is if this property, if this phenomena in some sense can be observed also for other kind of structures in the weight matrices, for example, structures of low rank. So we reproduce essentially the same experiment that reproduced in the original paper, but by using matrices of small rank. So essentially, here we're still counting the compression. So is the essentially the number of parameters we're counting in neural networks, which is related to the rank of the matrices, of course. As we can see here, we can use we can arrive to essentially using the same, so 2% of the memory in saving the matrices, representing them with very small rank, by essentially an extremely negligible small in test accuracy, for example, in performance. This is the same test case of the example on the left. So there is a question that arises, and the question is, it may be true for low rank matrices that the lottery ticket hypothesis is true, and the sparse one has been proven in different kind of papers and different kind of flavors. The low rank one has not, but there is a fundamental difference between these two cases here. And the fundamental difference is that here I'm showing it by an example. So here, essentially, I'm plotting the weight matrices at the end of training, a spy of the weight matrices, and I'm setting to black all the entries of the matrix which are in absolute value bigger than 10 to the minus 4, which is given a generous quantity. And the white ones are the one whose absolute value is smaller than 10 to the minus 4. And essentially, you can see here that at the end of training, essentially, these matrices here are non-sparse. We cannot say they're sparse, and even as I said already, 10 to the minus 4 is generous. While if we plot, for example, the singular values of the weight matrices at the end of training on the same task, we can see that, for example, for a very big network here, this is a 15-layer network. It's not necessary to use such big of a network, but we want to understand if in some way these structures, these low-rank structures, arise also in bigger networks. And as you can see here, essentially, there is a very big drop in the singular values around the value of 10, which is, I would like to make you notice, it's a number of classes of the classification problem for essentially all weight matrices of the neural network. So there is a fundamental difference. The fundamental difference is that it looks like that low-rank structures are naturally arising during training, while sparse structures are non-arising during training. And a following question is, can we quantify it? Can we prove, can we show something about what's the correct rank of the neural network? And this would have very strong computational implications. For example, I've been working on the first part of my PhD on trying to train low-rank neural networks for saving memory, for saving computational costs. And there is the first step one can take in this sense, say, I don't know the rank, the optimal rank in some way. And so the diagnostic path is to say, let's try to develop some numerical methods which are rank adaptive. So I don't have to choose, for example, if I have very big networks for many layers, I have to choose the rank for each layer, and it's a hard problem. It's very difficult to do. So one can try to develop adaptive rank algorithm to not have to choose a priori, let's say, the rank of every layer. As we can see here, for example, the computational advantages are huge because instead of having to train 180 million parameters, essentially, we have to train, for example, 0.7 million parameters with essentially even better performance than training all of them. And the speed up is even bigger compared to other rank adaptive methods like LoRa, the LoRa. I don't know if you're familiar with that, but this is a task of fine-tuning, essentially, which is in some way similar, correlated to compression. But yeah, so this was just to motivate, in some sense, why the question of the implicit bias towards low-rank matrices is important, and how to exploit it computationally. So if we could quantify what the optimal ranks will be, we would like to speed up even more, because there would be no need to use rank adaptive methods. In some sense, one could choose a priori the correct rank, in some sense, the optimal ranks, and would just optimize neural networks, constraining the weights to be in the correct rank manifold, essentially. And so this is the second approach: try to understand what these optimal ranks are. So this problem has been already studied in multiple settings, actually. There is a lot of literature, and a lot of people study this problem in the what is called the deep linear case. So essentially, it's the case in which the nonlinear activation are the identity. So they are linear in some sense. The network is linear from input to output, but it's nonlinear in the parameters. And the optimization, the function want to optimize to train the network is non-convex in any case, even if the nonlinearity are the identity. And so there are still some theoretical questions on this matter that people studied, and they've been able to show that there is indeed implicit bias towards low-rank structures in this case here. The question is, can we extend it to more real setting in some sense, in which it's interesting to study this problem from a theoretical point of view for deep linear networks, but to use a deep linear networks is no advantage because essentially we're just representing a linear map. So the nonlinearity is really the crucial point of why deep learning works. So we will denote with theta the set of our matrices, and we will define this loss function L of lambda, which is essentially simply we're trying to interpolate the labels of the classification problem with our last layer, and we're regularizing with weight decay, what's called weight decay, which is one of essentially the most used regularization in deep learning. And yeah, it takes this form here. So essentially, we're just summing the Frobenius norm of the matrix squared. And the observation is that the stationary points of this optimization problem take this form here. So we have that the gradient of the L0, so without the regularization at stationary points, is essentially parallel to the weights. And this is interesting because it allows to transfer properties from the optimal point, theta, to the gradient of the loss function on that point. So this would mean that essentially, for example, if we can prove some low-rank properties on the gradient, then we can prove some low-rank properties on the parameters. And essentially, this is what it's saying: at stationary points, the rank of the weight matrices is equal to the rank of the gradient of the loss created on the weight matrices, and for every layer. So essentially, if the gradient is of low rank for every layer, then all the weight matrices are low rank. And the L0 here, just this piece here, essentially this Frobenius norm of zeta L theta minus y squared, can be decomposed by columns, and it can be just written as the sum over the classes and the point over each class of the last output, the ith point of the kth class minus its label, essentially in norm squared. And the interesting point is here, if all points of the same class are collapsed in a layer before the last one, then essentially this gradient here will be of low rank. And so this connects two phenomena. Actually, one has been studied, which is called neural collapse. And here I'm presenting what's the connection then between this phenomenon of neural collapse, of which we'll talk a bit more later. Essentially, what we need to define is what we call the total cluster variation at layer L. So in intermediate layers, we want to define the total cluster variation. The cluster is the class in some sense, so it's intra-class variation. We have to define for layer L the centroids of layer L, which is nothing but the average, essentially, of all points in the same of all points in the class K at layer L. So we are taking our data points, we're mapping them through the neural networks until layer L. We look at the ones staying in the kth class, and we average them, and this is this centroid here. And the total cluster of variation of the features is essentially the how much these points, the points in each class, stay far from their centroids, averaged over the clusters also. And we have the following proposition, which here I've been writing as informal, but you can find a more precise version in this article, which I cited here. So in the setting above, if we look at stationary points and we look at the set of matrices with the rank smaller or equal than k, then we can bound the distance between the stationary point and the set of matrices with the rank smaller or equal than k. And we can bound it with this lambda to the -1, this constant here, ml of theta star, and the minimum of the total cluster variation of the layer before the L one. So essentially, what is this proposition is saying is that if the total cluster variation of some layer before the health one is 0, or it's very small, then the rank of the matrix, even a subsequent layer, is going to be of low rank. Now the natural question is, how small is the TCV of in general of a layer J? Because if we can prove that it's 0, for example, then yeah, we would have exact low-rankness of all the matrices after the layer J. This connects to what I was mentioning before, so the phenomenon of neural collapse, which has been first observed in the 2020. But it's essentially in a bit of different form in the one we need. So the empirical observation, I would like to mention also that neural collapse actually is talking about 4 different properties that happen during the training of a neural network. We're interested in the first one. There is the TCV of the layer before the last one is going to 0 during training, essentially. So what it's saying is that when the neural network starts interpolating the data points, then in the layer before the TCV is going to 0. And this has been proven in a variety of different works later using toy models, which is, for example, the most used one is the unconstrained feature model, in which essentially people study this optimization problem here. That's why it's called unconstrained, because essentially we're looking just at the last weight matrix, and the rest we're treating it as a free matrix. And can be proven that the stationary point of this optimization problem actually satisfies this property here, that the TCV of Z goes to 0. The problem is that this model is far from what happens in reality with real neural networks, both because of the fact that Z here is unconstrained. So essentially, the idea here is to think of Z as the backbone of an infinitely deep neural network or a very large neural network in some way. So we can move the matrix Z as we wish, as we will. And there is this regularization term here, which doesn't appear on weight decay. And I would like to mention also, maybe I didn't do it before, that weight decay is actually crucial to observe this low-rank phenomena. I've been showing it in the slide before, actually, but in general, there is a lot of examples in which numerically you don't observe low rank if you don't have weight decay, so if lambda is equal to 0. Okay, so this model is, the problem is that this model is far from reality, and the problem for us is that it doesn't say anything about the collapse of intermediate layers. So this says something just on the TCV of the layer before the last one, but this would imply for us just that the very last layer is low rank, but it's already obvious because it's mapping from a space to a space of dimension k. So in our sense, it's already low rank. So the question is, can we try to extend this theory for a more a realistic setting and extend it to the deep version of neural collapse? The deep version of neural collapse has been indeed studied already in different works. It was observed first in this paper here of 2023, and it was proven, it was studied in different works, still using extensions of the unconstrained feature model for multiple layers. So yeah, essentially it has been proven also for this deep unconstrained feature model case, or in cases in which essentially you switch off all the nonlinearities but the last one, which is still far from ideal. So first of all, the question is, yeah, it's been observed in other works, but I would like to show you that actually this TCV, total cluster variation of the layers before, goes to 0. I would like to show it to you because yeah, I feel like it's a singular phenomena. So what I'm going to do here is I'm going to take the matrices here, my matrix is ZL during training. I'm going to sample a random matrix with orthonormal matrix of this kind here. So 2 features I'm mapping from the space of dimension NL to a space of dimension 2. And I'm essentially projecting down the features of ZL onto this 2-dimensional space. And I'm going to be plotting the columns of this matrix ZL here, and I'm going to be coloring them depending on their class. So yeah, so all points of the same class in the health layer is going to be represented with the same color. So this is the situation of what I was saying before. So these features randomly projected on a random two-dimensional subspace, essentially, for all layers of a 15-layer neural network. This is at initialization. So we're not interpolating. The last layer here is not interpolating the labels, and everything is mixed up even into this two-dimensional subspace. Here is, as training goes on, I'm going to show you every 100 iterations of optimization, essentially. As you can see here, the network is starting to cluster. It has to cluster in the last layer because of how essentially of why is made, why is collapsed. In that sense, in the sense I was talking before, the total cluster variation is 0 of y. So to interpolate, it has to go TCV 0. And when going on, we can see that the last layer goes even more collapsed, and the one before start collapsing also, which is a singular phenomenon because it's, in my opinion, it's non-obvious from the optimization problem we're trying to solve that this representation would be optimal in some sense. And as training goes on, the features continue to collapse, continue to align actually on lines, on lower dimensional objects on this plane here. And then they essentially all collapse to points. So this is a random two-dimensional subspace, but in this two-dimensional subspace, the points are the TCV of the total cluster variation essentially goes to 0. And I wanted to show this example here because I feel like it's more pictorial, gives better the idea of what's happening. But actually, the TCV goes to 0 for all layers, even non on a two-dimensional subspace, but in the full space. So this is just pictorial. So after having shown this, I wanted to talk about a bit about our last research progress on how to try to go beyond the unconstrained feature model. The idea here is to switch the attention to feature space instead of from weight space, and to study the minima of this what's called the L2 representation cost, which has been used in a lot of papers, for example, in this one here, in which the author studied this representation cost here. And they, even in this work here, they propose to switch attention to feature space. And I would like to mention also that this representation cost here essentially represents our loss function L of lambda for lambda very small. It can be proven, it's not that complicated actually, that a rescaled version of L lambda, so lambda to the -1 and lambda, actually gamma converges to this function here, R of theta. So in some sense, the minima of our L lambda are close to the minima of this R theta here for lambda very small, which is the practical regime because it's the regime that people use in deep learning, as I mentioned before. Weight decay is ubiquitously is basically used in almost every deep learning application, and it's always used very, very small value of the hyperparameter lambda. I would like to mention also that this deep linear representation cost can be actually studied analytically for the deep linear case. That's been done also in different works here, Site 1, for example. And essentially, the minima of this L2 representation cost is so the minima. Yes, it's a rescaled version of a Schatten-2 quasi-norm. So essentially, it's this is an LP norm in the space of on the singular value vector. In fact, it can be written like this. And this actually, the minimum of this representation cost in this case here not only implies that the intermediate layers are collapsed, but also implies that gives insights, at least in deep linear case, for Y for big L, for example, there is a sparsification effect in the singular values of the product matrix. Because yeah, if L goes to infinity, essentially this converges to the rank of the matrix, which is it's the support is the L0 pseudo norm. Okay, so let's go to the nonlinear case, the nonlinear setting. The idea, as I said before, is to switch the attention to feature space. So we have our matrices WL plus 1, and we want to would like to look for the WL plus 1 of minimal norm, which essentially represents the layer. So maps ZL in ZL plus 1 through itself and the nonlinearity. And this essentially is given by assuming that the nonlinearity is invertible, is given by this expression here. So it's sigma plus 1 to the minus 1 of the layer after, multiplied by the pseudo inverse of the feature matrix before. There is a constraint, however, that needs to be taken into account when doing this, and it's this constraint here, which is natural. When we multiply this expression on the right by ZL, we get WL plus 1 times ZL, and we will like that it returns this sigma plus 1 to the minus 1 of ZL plus 1. So this is a very natural constraint that we'll see later, but essentially it's just saying that when doing this, we can exactly represent the layer after. So this WL is actually able to represent the layer after. Otherwise, we could represent something which is not a neural network in the sense we mentioned above. And so, as I said, we switch the attention to then this representation cost here, which is essentially the previous representation cost written in terms of this new parameterization. So instead of WL, we put inside the representation cost this representation here of the weight matrices. And the question is now, can we study the minima? Can we say something about the minima of this representation cost here in feature space? And what I would like to make you notice is that on this example here, I'm putting weight decay. I have a big L layer, and I'm using weight decay on no layer but the first one. Because what I'm going to be showing later is that if we have a sequence of layers, essentially all with weight decay, and the first one doesn't have weight decay, then there's going to be collapse on all the layer after. And in fact, the crucial point is to observe that the first term in this representation cost here depends just on Z1, and it's possible to characterize the constraint minima of the first term essentially. So this sigma 2 to the minus 1 Z2 Z1 pseudo inverse in Frobenius norm squared. It's possible to characterize the minima Z1 star, there are infinitely many minima, but it's possible to characterize all of them. And with certain constraints, including then this natural one, all the feature matrix has to satisfy this property here. So essentially, when we do the scalar product between our points, the embedding of our data points in the L layer, this has to be proportional with the gram matrix of the layer after before the nonlinearity, however. Okay, so pictorially, I would like to show also this what's going on actually, and convince you in some way that this is actually what's happening. And I'm gonna be doing this by exactly plotting the feature gram matrices of the same neural network before, so 15 layers during training. So this is at initialization. You can see there's no structure. We're not interpolating here. We're very far from Y because Y transpose Y has a block diagonal structure, actually, depending on the classes. Here is after 100 steps of optimization. As you can see here, maybe we're not already interpolating, but this block structure, let's say, emerged from training, and also started to appear that there is a similar structure in all the weight matrices before, but the first one for the reason I mentioned before, so that we're not connecting this to the first and the second layer with weight decay. We're connecting all the others after. And this as training goes on, essentially we start to see here we're interpolating already. So we're essentially with the first term of the loss, which has a value of around 10 to the minus 5, 10 to the minus 6. We continue, we go on with training. And we can see that actually the gram matrices are aligned with each other, proportional to each other, and that's what I was claiming before in the slide before. So there is this. It's possible to characterize this minima, and it looks like, from an empirical point of view, that's what happened in practice, apart from the last layer for the reason I said before. So I would like to talk now a bit about our main result. I would like to mention also that this is work in progress, but hopefully will come out very soon. It's possible to characterize and prove that the deep neural collapse, the first property of deep neural collapse, this is how it's called, so the TCV goes to 0, is optimal for consecutive layers with weight decay. So in the setting above, in which we're using weight decay on a sequence of layers, but the first one essentially, we look at the global minima of the representation cost with the natural constraint I mentioned before, so the representability of the layers in the neural network format, and we put a constraint on the ranks. We put that the rank of each, essentially each matrix before nonlinear activation has to be bigger than the rank of the last matrix. And the third condition is a condition which is still work in progress, can be relaxed, most probably. But essentially, it's a constraint, and it says something about the nonlinearity. If the nonlinearity, for example, is bounded, it's not really possible to represent all singular values. So there is a bound on the singular values in some sense, or a bound on the norm in general. And the main result is that the global minima of this representation cost here with this constraint here are exactly collapsed for all layers that go from the first to the last one. So we're interpolating on the last one. It's obvious that it's collapsed, but it's true also for all the layer below. So this is essentially connecting it to the previous result, is saying that for small lambda, it's optimal to have TCV of J equal to 0 for all layers before the last one. So in some sense, this is a step. It's a step towards extending deep neural collapse theory for the nonlinear setting. Okay, and this is true for essentially all invertible nonlinearities, and it's true if, of course, the last layer, as I mentioned, the last layer is mapping a space of dimension k, and we need a pyramidal architecture. So essentially, the width of the layers is decreasing, and we need the first one to be big enough. We need to be at least the number of data points. This is reasonable in the sense that with this hypothesis here, we are allowing the neural network to make the features collapse at the very first layer. And this is essentially saying that if we can do that, then it's optimal. And this can be relaxed also. The constraint can be relaxed, but it's in progress work, as already mentioned. And these results here can be extended even in a more simple way for ResNets, even with weaker constraint. You can get rid of the majority of the constraint, essentially just leave the natural constraint on the representability. And for ResNet, it's already true. But this leaves already, apart from trying to relax the result, leaves another question open. And the question is, okay, it's true. We showed that the global minimum of the representation cost satisfy the deep neural collapse property, so the TCV is 0 for all layers, essentially. But is it really possible? Why? Still doesn't explain why this phenomena is so consistently observed, because it's the loss landscape, it's highly non-convex in general. So it would not explain why, in some sense, then we're converging always to global minima. And still in this setting here, but can be hopefully extended in a more general setting. If we allow all layers essentially to be of the big dimension n, which is bigger than k here, I didn't mention, but here we're working a classification problem in which we assume that the number of classes is bigger than the number of data points, which is the classical, in some sense, regime. Then for every initial condition, which satisfies the constraint, and which is interpolating, so when the neural network brings already to an interpolating condition, then there exists a continuous path, gamma of t, which lies in the constraint, which starts from the initial configuration, whatever it is, and whose final point lies in the minima of the representation cost. And this essentially is making the representation cost decrease. So this is saying that not only the global minima satisfy deep neural collapse, but if the layers are large enough, and we can say how large, then in the previous setting, there is, we can, in some sense, from every initial condition, despite the non-convexity, we can find a continuous path which makes the representation cost decrease, which brings us from whatever initial condition to the global minima of this representation cost here. Yeah, and this is another hint on why this deep neural collapse phenomena is so observed. And why also this low rank implicit bias is is so observed in deep learning. I'm done. I'm a bit early. I hope I won't offend anyone. And thank you for the attention. I'm open for question, discussion, or whatever.
Thank you, Emanuele, for your nice talk. Now, moment for the question. Any question? Please come here because the microphone.
Okay. So thank you for the talk. Very, very interesting. I actually have two questions. So the first one is regarding the sparsity pattern that you showed at the beginning.
Yes, sir.
So the sparsity pattern, from what I understood, are for MLPs, neural networks. So this is more a curiosity than a question. Do you think for equivariant networks, or anyway networks that impose some kind of geometrical constraints, these type of patterns could also be formed, or do you have any intuition? And
yeah, you're talking about sparse patterns, though, right?
Yeah.
Okay. To be honest, I don't have much intuition on this, but I wouldn't exclude that some kind of sparsity patterns are arise during training if some kind of symmetry is imposed. Of course, it highly depends on which symmetry is imposed. But to be honest, I don't have a clear answer to that. I'm not sure. Cannot give you an example, for example, which I'm sure that would arise.
And then the second question actually was more related to your methodology and feature collapse. So from what I understood, it can work with basically any loss function because that depends on the parameters theta. And then you show some experiment on classifications, which at least to me, it would make sense that some cluster would form in the feature spaces because at the end of the day, you are choosing classes. So it should clusterize, so the TDV should go to 0. I mean, theoretically, I'm sure you prove it, but at least if I think about it, it makes sense to me. But have you tried using, for example, language models in which you still have a problem that you need to solve, but it's one too many? So in that case, it's not a classification problem, and it would be interesting to see if features also collapse in that sense. So this is more a question, or if anyone. Yeah. Thank you.
First of all, I would like to precise that here the loss function is general up to a certain point because there's L2 regularization, but here I'm using L2 loss because we can prove things for the L2 loss. Even though this is not optimal actually for a classification problem, majority of the time people use cross entropy. But in some way, if we can interpolate, then we're classifying correctly. But actually, all this theory holds for classification problems. So we need Y to have that kind of structure. I believe something relaxed can be said for other kind of problems, but I wouldn't expect, for example, I don't think it's even observed that there is exact collapse of the features for more complicated architectures, more complicated tasks. And also regarding your first observation, yes, it's intuitive that you're trying to classify essentially. So it's intuitive that some kind of structure arises in the feature spaces. So the points are in some way clustering during, let's say, moving on the layers. But it's not obvious that, for example, if we turn off this way decay here, the clustering would not happen essentially in non-determinate layers. This can be shown just by doing a numerical experiment with the lambda equal to 0. This doesn't happen, and it's not obvious also that it will collapse immediately from the first one if we give him the chance to. So yes, but thank you for the observation. And actually, we're trying to extend these relax a bit the results for even let's say non-hard classification tasks, but it's a bit more challenging and maybe for future work.
Thank you for the answer.
Any other question? Also from online. Okay, I have a curiosity. If you have to explain to a child what is the total cluster variation, how can you explain that?
Sorry, if you have, I didn't understand the first part.
If you have to explain to a child what is
Yes.
the cluster variation,
Yes.
how can you explain that?
It's essentially the variation. I mean, to a child. Okay, so essentially, if we're on the same page on what's the mean, this centroid, the class centroids, I'm assuming that that's okay with that. So essentially, we're taking we have all our, let's do an example for the first class. So we're looking at all points belonging to the first class. We're mapping them through the neural networks until the alpha layer. We're looking at all of them. We're taking the average of them, and this is exactly essentially the centroid. And then the total cluster variation is a measure of how much all the other points in this cloud here in the out layer distance from its centroid. And this is done for a single, I gave you this explanation for a single class, and you average also the same for over the classes. So essentially it's a measure of how much the points are concentrated in the health representation space in some sense. So we map all the data points through the out layer, and we look how much the points in the same class are concentrated along around their centroids.
So at the end, it is a form of barycenter or a barycenter or a standard variation.
The centroids is essentially the barycenter, and the TCV is telling us how much the points are distant from the barycenter.
So at the end is a standard variation, I think.
Yeah, it's a standard variation, yes. It's actually essentially a standard variation.
Okay, thank you. It was just a curiosity because I'm not of the field, so I'm trying to understand what you have done and you have conceived this sort of stuff. Okay.
Thank you. Thank you. You're welcome.
Any other question?
Just a little curiosity. Can you hear me?
Yes.
Okay. So I was curious about the dynamical part of the clusterization of the feature space. So I don't know if you have done some studies about, okay, we have a scene convergence. So the feature space arrives to a clusterization in some sense, but about the dynamical part of how to reach that clusterization, is that some studies about this part? I don't know if it's clear to you.
Yeah, I understand. The point I think is that it's there are some studies, for example, in the deep linear case, but it's very difficult to characterize the exact dynamics on which the cluster arise, essentially. And this is the reason for which we, in some sense, doesn't prove anything on any, let's say, we didn't impose any dynamics in this theorem here, essentially. It's just an existence result that there is a path that connects from initial condition to clustered representation, essentially. But this kind of results moved from dynamics to existence allows to, in some way, give a result which is independent of dynamics. So it's even, some sense, maybe it's more general, but it also allows to avoid studying precisely dynamics, which is extremely complicated. And yes, so as far as I'm concerned, there is no result in the nonlinear case and about the dynamics on which the cluster arises.
Okay. Thank you.
You're welcome.
Okay, so just one very quick curiosity. So if you go back to the slide where you showed the theorem in which you bound essentially the distance to the low rank matrices with the lambda to -1.
Yes.
so in that slide, so here exactly here. So here you are bounding in the so the norm that you consider in the left hand side is the L2, the standard L2, right?
It's for B news, yes.
Right. Yes. Sorry for this. And say, can you study also? So this is one quantity that tells you in let's say in that kind of space how distant are these matrices. But since you're also interested in some kind of patterns in these matrices, let's say, can you do something like that for other norms that somehow privilege some kind of sparsity pattern or some other things in, let's say, could this be an interesting question to ask? Say.
Yeah. Yeah, this is a very interesting question. I thought about it, about trying to extend these results actually for other kind of norms. Let's say, I think, as I can remember from the proofs, I had the impression that it could be extended for any matrix-induced norm, for example. But the problem is that, as you correctly said, when we're interested about patternizing, let's say the optimal norm one would like to look at, for example, is maybe for low-rankness, no, it can be even another one actually. But for example, it could be like the max norm, and I believe that in that setting, a result of this kind here cannot be proven. I'm not sure it can be proven.
Because it would be interesting to understand how in different norms, maybe you may have different dependence on lambda. So now here you have 1 over lambda, but let's say for a different norm it could be different. I don't know. I'm just guessing some kind of different.
No, personally, I believe that this constant here would change. The total cluster variation would change in some sense, in the sense that most likely the norm here inside the total cluster variation would change. So it would not be a 2 norm anymore, it would be something else. But I think that for any norms you try, you cannot get rid of these lambda to the -1, at least for the proofs we followed.
Okay. Thanks a lot.
Thank you.
Any other question? Also from online? Okay, that's all. So let's thanks again, Emanuele.